Okay, thanks, Justin. I assume you can hear me.
Yep.
I'd like to thank everybody for joining in today, and especially Justin for inviting me. What I'd like to do today is actually talk to you about two different research projects I have ongoing, and I think they're the two that relate most strongly to operational meteorology, and they both really involve severe thunderstorm winds. So in effect, today you're going to be getting two talks in one. And so I'm going to start by discussing a NOAA-funded project titled A Machine Learning Tool to Provide Probabilities that Severe Thunderstorm Wind Damage Reports are due to winds of 50 knots or more. And this is a collaboration with some statisticians and mathematicians, along with Israel Girak and Adam Clark down in Norman. And then I will close talking about an NSF-funded project that's looking at differences between severe and non-severe warm season nocturnal bow echo environments. And this is work being done by a master's student, Ezio Mauri. So with regard to this NOAA project, and I'm not sure if any of the people on this call participated in the hazardous weather test bed. If you did, then you're going to recognize some of what I'll be discussing here. But really the nature of the problem, and I believe I'm preaching to the choir here, is if you use, for instance, the most recent 12 full years of data that we had available when we started last year, so from 2007 to 2018, and you look at all the storm data, thunderstorm wind damage reports, out of over 180,000 reports, 89% do not have a measured wind value associated with them, so they're given an estimate, often days later. And if you look at the roughly 20,000 measured reports and you go knot by knot and you compare the distribution to the actual estimated ones, you find that 40% of all the estimated reports have a value exactly of 50 knots. There's another 25% that are assigned exactly 52 knots, which is 60 miles per hour. If you look at the measurements, you have 13% that have a value of 50 and 13% as well that have a value of 52 knots. So clearly, human factors are entering the picture here with, an extremely large number getting assigned a value exactly 50 knots or 60 miles per hour. So our NOAA collaborators down in Norman, along with some of the Weather Service offices where I've talked with people, have told us, it's generally believed that many of the damage reports, especially those involving trees, have overestimated wind values. Because there are many reasons that trees or limbs can be blown down with winds well under 50 knots. This also fits with a study done by Roger Edwards and some colleagues in 2018, where they showed in wind tunnel tests, people tend to overestimate 60-mile-per-hour winds by 25%. So they basically acknowledge that people are terrible at estimating winds, and this actually implies that every estimate up to 72 miles per hour might be sub-severe if people were just judging it by what they felt. Now, we realize most of the estimates in storm data are because of the damage done. Machine learning has really taken off in meteorology as a forecasting tool, especially in just the last few years. And to have it work well, you have to have an accurate ground truth database for the training. Otherwise, your forecasts are going to be wrong because the machine learning tools are going to just be telling you what the conditions were like when somebody called in a tree down report and not really giving you an idea when truly 50 knot or greater winds are likely to occur. And in addition, the problems with the verification database actually impact both verification of SPC outlooks and National Weather Service warnings. So our approach, and this is really, this whole idea stemmed out of discussions with Israel and Adam down in Norman. We're using 6 different machine learning techniques. 3 are basic methods. One is the gradient boosted machine, known as GBM. Another is a support vector machine, SVM. And then neural network, which might be the one most of you are familiar with. And then 3 ensemble methods, which include stacked logistic regression ensemble model, the stacked random forest, and just an average ensemble model. So we've been looking at all 6 of these and using as a training data set either all the reports from 2007 to 2017 or 2007 through 2016, and then testing on the remaining year or two. So 2018 ends up being within the test set, no matter which approach we take. We end up taking date, time, location, and then all the text material. So that would be the event narrative and episode narrative from the storm reports database. And we're also supplying the algorithms with the distance of any report to the nearest measured report. So what we end up doing then is for the over 180,000 reports that were showing up in this 12-year period, we then input also SPC mesoanalysis parameters. Now these are on a 40-kilometer grid, if you're not familiar with it, that are based heavily on the RAP and RUC analyses, but then some current OBS are also analyzed into the RAP or RUC analysis. And we used this as input. We selected 31 weather parameters based on the ability, from our understanding of what causes severe winds and thunderstorms. We picked parameters that seemed like they might be good judges of this. And we input it over a 5x5 grid, so a 200 by 200 kilometer box, roughly centered on each storm report. We didn't want to just take the weather data for the location of the report, because we wanted the machine learning to also maybe have a feel for how things vary. If there's a cold front coming in, for instance, the machine learning might see, oh, there's cool air to the west in a lot of these cases, and warmer air to the east. So the 31 parameters generally relate to instability, things like CAPE, SIN, and lapse rate, wind shear, and some actual wind values or averages and layers. Same for relative humidity, and some of the composite parameters. Now, with the GBM approach out of the 6, it was relatively easy to do a quick parameter importance test. So, our preliminary results for that find that some of the parameters that seem to get the most weight, that seem to work best at helping predict the probability that a storm damage report is due to severe wind, include the distance to the nearest measured report, which makes sense, the text data, the event and episode text from storm data, along with the Evans-Derecho composite, downdraft CAPE, and mixed layer SIN. And those first two, if you think about it, I mean, I think we all realize, yeah, those kind of were created to try to predict the likelihood of severe wind. And then mixed layer SIN may tell us something about the ability of the wind to be able to make it down to the ground. So I want to talk a little bit about some caveats before moving on. We found, it was surprising, and maybe you would fall into this camp, a lot of people believe that the storm database only contains measurements and estimates of 50 knots or greater. But it turns out that's not true, which is fortunate for us. 98.5% of the storm reports have 50 or greater knot winds associated with them. But that does leave 1.5% that are subsevere. And if you're going to be training machine learning algorithms, you kind of want the machine learning to know what the environments are like when the winds are not severe. In addition, as of now, we've excluded about 2% of all the reports because the duration was over 20 minutes and there was insufficient information on the best lat or longitude to use to define where the storm report is. And finally, some of the 31 SPC mesoanalysis parameters that we chose do not exist for the first few years in the database. So we currently give those missing values, and machine learning is supposed to know how to deal with that. But we're going to be continuing to look at tests where it might be able to get a better performance by simply not using those at all. And in the future, I want you to know we're currently working on grabbing population density data to use as input, because we think this may influence the likelihood of damage to get reported, and land use data, just in case it might be easier to get tree damage when forests are everywhere, as opposed to, say, western Kansas, where trees are few and far between. And in this coming year, we're going to add radar composite reflectivity and azimuthal shear data over roughly a 50 by 50 kilometer region centered on the storm reports. Now you might say, well, wouldn't the velocity data be the best thing if you're interested in severe thunderstorm winds? But there is no good national data set existing of velocity data because of the challenges with only having the Doppler component, the single component of the wind, which of course varies depending what is your nearest radar. But we think that the reflectivity data should help the machine learning techniques to infer storm mode. And we've been in touch with Alex Haberle, who published a paper in 2018 where they used machine learning techniques to diagnose storm mode for every report in the storm data that had a severe weather report. So again, these are things we plan to be doing to add to the system in the next year. So the initial tests, even without radar data, looked actually very promising to us. We looked at the area under the rock curve and the Brier score, and these did suggest some skill when using just the measured reports. So to train the data and then to test it, we had to only use the 20,000 measured reports because those are the only ones where we have ground truth measurements available. So the table here, I'm not going to talk about much in the table, but this is based on training over an 11-year period and then testing on 2018. And I circled in red the best skill scores. And so the average ensemble on the right tends to have one of the best areas under the rock curve of about 0.85 and a Brier score of 0.145. Generally, the lower the Brier score, the more skillful the forecast, the higher the area under the rock curve, the more skillful. So the average really stands out as doing a good job with both. The stacked vector method off more toward the left had the highest area under the rock curve of all, whereas the stacked GLM ensemble approach had a slightly better Brier score even than the average ensemble. So we had some objective measures of skill. If you're not familiar with area under the rock curve, generally if the value gets above about 0.7 in the literature, people have said that that shows it has some skill. Okay, so prior to the recent tests that we did with these algorithms down at the spring forecast experiment, we did a study grabbing 8 different events that took place in 2018 that had variations in the peak probabilities of severe wind that were issued by SPC. And we wanted to try to see, might it be that our algorithms are more confident that storm damage was truly due to severe winds in the areas where the SPC forecasters were also more confident that severe wind would happen. So this is one example from early May 2018. In this example, we use squares for the estimated storm reports. We use triangles for the measured, and we use a shading of blue that's on the right side for the probabilities coming from our algorithms. So in this case, you know, the SPC was pretty gung-ho, especially over Kansas and Missouri. And in the plains, a lot of these reports, whether they be estimates or measurements, are getting dark blue values. So the algorithms felt pretty confident they were from truly severe wind. And what you can see in this case that's kind of interesting and maybe nice to see is reports that were tending to fall outside the area that SPC was interested in, like those in southern Missouri and northern Arkansas or Michigan. The algorithms spit out values were pretty low for probability. So maybe implying that those really weren't from severe wind. Here's another case. I chose this one because I want to highlight something that we have been observing often, and I think it showed up a lot in this year's SFE, is the algorithms seem to produce higher probabilities for events that happen in the central US. So in this chart, there's a lot of dark blue in especially Nebraska down toward Kansas City. But if you look in the east, there's a lot of estimates, a lot of storm reports that took place that were most likely trees down. And in this case, this particular algorithm gave low probabilities to the vast majority of these reports. Now, you know, we're having to give a lot of thought to this. So this is matching what a lot of forecasters told us that they believe. But in some ways, I almost feel like it's matching too well. I'm questioning, should there really be such overabundance of low probabilities issued for so many reports in the East? One other concern, and if you're not aware of this, is in the United States, the vast majority or a greater chunk of the measurements for severe wind end up happening in the central part of the country. Measured reports of severe wind are more rare in the East and in the West. And so one of the things we're going to be looking into is, could it be that because there's less training data for situations in the East where you have maybe wet microbursts, so perhaps a more moist sounding than you get in the central US, is it just that the algorithms are so used to seeing conditions from the central US that they automatically assume the environment is not good in the East? You know, these are really difficult questions to answer. So in this study of the 8 events in 2018, we averaged them all together, and we found that yes, the higher the forecasted probability that SPC gives, then it turns out when the storm reports happen, our algorithms are also assigning, in general, higher probabilities that the reports were due to truly severe winds. So, if you think about it, this whole issue is a very challenging one because there is no ground truth for the estimates. In fact, the machine learning people on my team from statistics and math, they were laughing, I think, initially when I brought up that this is what we need to do. And they chose the 6 algorithms based on ones that they felt do pretty well in these strange circumstances like this one, where there really isn't a ground truth to know what's happening. But one of the ways to get an idea if the results are reasonable is to do a chart like this. As long as you assume the SPC forecasters are kind of skillful at what they do, it would make sense that the atmosphere is more likely to truly produce severe wind when SPC thought from the forecast that they better have higher probabilities out there. So during the spring forecasting experiment that just got done about a week or so ago, we decided to have the participants evaluate 4 of the methods. We chose 3 based on the fact that they had done pretty well in the objective scores. And we also tossed in the neural network, just because that's sort of the most famous machine learning method, and everybody seems to be at least a little bit aware of neural networks. We created a website to create a display of the output similar to those 2018 maps I just showed you, with the estimates having squares and the measured values triangles. The output was available in real time. So every day by 10 a.m., we had the probabilities up from the previous day's storm reports. And here I said there were probably at least 50 participants evaluating our algorithms for at least 2 days, each of the 5 weeks. It might have been closer to 100. I just haven't looked to see who all did end up participating. So one of the cases this year that demonstrates this issue in the East is this particular map. So you can see SPC was not very excited. And by the way, the outlooks that we have overlaid in all of these maps were from 1630Z. So in this case, you see most of the estimates, whether they be in the white regions that were less than 5% probability or in the light brown, which is the 5 to 15% chance, ended up getting low probabilities. The one estimate that fell in Texas within a slightly higher zone of the SPC forecast did end up getting a somewhat higher probability. So if you've ever been in the spring forecast experiments, one of the unique things is it gives you the opportunity to gather some subjective evaluation scores. So we had all the participants evaluate on a scale of 1 to 10, how reasonable, how accurate did they think the output would be. Obviously, this is a challenge, as I mentioned, because there's really is no ground truth out there. But the 4 algorithms scored relatively well, relatively similarly, kind of close to a value of 6. The average ensemble earned the highest subjective scores. That matches our data showing that it did best objectively in 2018. Maybe the one surprise here is people rated neural network a little bit better than GBM, whereas the neural network tends to do the worst with the objective scores. However, the ratings varied by week of the project. So this is sort of a noisy graph. The colors refer to the weeks of the SFE this year, and the 4 different sets of bars refer to the different algorithms. If you look on the left side, GBM actually had some of the highest scores of all in the first 2 weeks. In fact, it was judged the best algorithm during those first 2 weeks. Then it switched and it was judged the worst algorithm the following 3 weeks. So this could be a function of the particular people participating or the type of weather events that took place. And we're in the process of analyzing some of that data. One of the things we have discovered, which is quite interesting, whether it be a measured value or an estimate, people tended to give a higher score of how well they thought it was doing when the algorithms were printing out higher probabilities that the reports were truly from severe winds. So this might reflect a bias among the community that when we see a report, we just want to trust that, oh yeah, that probably was from severe wind. The GBM tended to produce the greatest range of values. It often created really low probabilities for some events, lower than the other ones, which meant that it often had people assigning it really low skill scores. So this is kind of interesting, getting sort of into some psychology here that we have to think about too. One thing we think is encouraging is we decided to separate out the measured reports from the estimated ones and see what were the average probabilities being assigned by the algorithms. So the yellow bars would be the measured reports, the orange ones would be the estimates. Now, some of you hopefully are thinking about this. If it's a measured value over 50 knots, then if the system is working perfectly, it should be giving it a 100% chance of being from truly severe winds. But if you know anything about machine learning, it's not so easy. If you really focus on getting it to do that for the measured reports, you end up overfitting the data, and it ends up performing worse for the estimates. So in this case, it's encouraging. It does know that the measured reports are more believable than the estimates. And if you see the GBM on the left, the GBM is the stingiest with assigning probabilities for estimated reports. So where do we go from here? Well, most of the participants in the SFE agree that there is a problem in the database, and they could actually see the value of the tool. In fact, after the project took place this year, SPC already told us that they want us to see how the practically perfect progs would differ if instead of assigning a weight of 1 to all storm reports, which is what is done now, we use for the severe wind estimates the probability values that come from our algorithms. That would change the practically perfect progs. And when those get compared to what the SPC forecasters issued, it might make a difference in how they are judged for a particular forecast of how skillful it is. But I'm going to acknowledge here the implications of using these algorithms are really substantial and raise major philosophical questions. So some of these are things that participants brought out. Is 50 knots a magic number for severe? You know, should we be obsessed that we really only want severe to be 50 knots or more? If a tree falls from 40 mile per hour winds and it hits a house, it is still a severe event for the homeowner. In addition, some forecasters right now probably issue warnings counting on a tree to fall to verify it. I know I've done this when I participate in the SFE, but other forecasters are truly aiming for only those storms that have winds of 50 knots or more. And so if this tool gets implemented, it's definitely going to impact the issuance of warnings and would require retraining, at least in some cases, for those people that right now issue warnings because they feel like, well, somebody certainly is going to have tree damage. So in the next year, as I said, we're going to be accessing terabytes of radar data to include in the training. We are performing tests to see the impact of training separate models for different regions of the country. And this again is in case the smaller number of measured values in some regions unfairly biases the output against weather conditions that truly produce severe wind in these regions, which might differ from those that we're used to seeing here in the central part of the US. And we're also going to examine the performance of the algorithms on a separate test set that we created using ASOS and AWOS data, where we have thunderstorms reported, and then we look at the peak wind associated with the storm. So we've designed that database to have the same number of severe and sub-severe wind measurements because we were worried about that lopsided nature in the storm data. But I do have to say, during the SFE this year, I was actually shocked at how easily the algorithms produced low probabilities in especially the East. The fear was, since in the training, all it ever saw was primarily truly severe wind, that it might be stingy at assigning low probabilities. That did not appear to be a problem, but we're going to go ahead and test on this other data set. Okay, so I know there's probably going to be a lot of questions on that, but I think the way this is designed, I just want to spend about a quick 10 minutes on the second research project, and then we have a time for questions about both. So the second research project is really looking at nighttime bow echoes. We know that severe winds and bow echoes may involve both having a strong surface mesohigh from the cold pull and downward momentum transport. And both of these could actually be more difficult to achieve at night than during the day because we tend to get the nocturnal stable layer right near the ground, which when I teach my students, I say it's like laying a mattress down or putting a cushion near the ground that makes it hard for the severe wind to plunge down from the storm and reach the surface. But we do know that many severe wind reports do happen at night. So this project is looking at 43 near storm environmental parameters to see if there are differences in the parameters for bow echoes at night that fail to produce any severe wind, and those that produce maybe only marginally severe wind, and finally, a third category, those that produce high intensity wind, at least one report greater than 70, and this should actually say 70 knots, so that's a mistake there. So using radar data, my student picked out 132 events that clearly had a bow echo. They happened all between 1 and 11Z, and I think all but one of these cases was actually after 2Z or later. And we ended up with a pretty equal data set, 44 events where there was no severe wind report within 6 hours of either side of when the bow echo looked best on radar. These are shown on this map in blue. A roughly similar amount only had marginal severe wind. These are low intensity severe, LS, which are shown in green. And then finally, 41 events had at least one wind report above 70 knots. These are called high intensity or HS and are shown in orange. So from the map, you can see the vast majority happen in the central US, and the dots, the colored dots, are pretty well scattered among each other, so we don't feel like there's a bias in the severity level based on the region of the country. This shows the distribution of events in our sample. We decided to use 5Z as a threshold and do some of our testing, breaking the data set into two, because events that happen prior to 5Z, the evening events, are still maybe benefiting from the high CAPE that built up during the daytime. So we wanted to make sure that these forecasting rules that we're trying to draw out of the data set might apply whether it be evening or whether it be late at night / early morning. So doing something a little dangerous here, just so you get an idea of what we were observing a lot. We created average soundings for the 3 severity classes. So we had to do some interesting things down near the ground because it's really difficult to do average soundings when the surface varies. But the main thing I want to point out in these 3 average soundings, if you take a quick look at this, what you're going to see is the pink area, the CAPE, is really what seems to vary a lot between the bow echoes that don't produce severe, those that produce low intensity, and those that produce high intensity severe. If you look at the SIN in the blue area down near the ground, or if you can look really close at the red line, which is actually the temperature curve near the ground, you find there really is very little difference in SIN or some of the details of the near ground stable layer between the cases. I went into this project thinking that that might be the holy grail, that whether you get severe wind or not is going to be a function of how stable it is near the ground. That does not appear to be the case. So I'm going to quickly go through a bunch of charts like this. The 3 colors refer to the 3 levels of severity, and we sort of group them by some general characteristics they tell us about the atmosphere. So in this case, we have on the left side surface-based CAPE, most unstable CAPE, and the 100 millibar mixed layer CAPE. And we actually find all 3 of these work really well and have statistically significant differences between the 3 severity types. In the middle is downdraft CAPE. That actually seems to work relatively well too. On the right side, surface-based SIN, most unstable SIN, and 100 millibar mixed layer SIN don't really vary much at all among the different severity types. For CAPE, this is a parameter in particular that might vary between evening and late at night. On the left, I'm showing, again, the same type of graph for the cases that were before 5Z, and on the right side, those that were 5Z or later. And generally, using CAPE works pretty well for no matter when you are having your event during the night. The thing that doesn't work so well late at night is the downdraft CAPE. So on the left set of figures, there's a big difference in the downdraft CAPE among the severity types, but on the right side after 5Z, downdraft CAPE has much smaller variations. Relative humidity, I think we all learned that dry air down low can really help get a strong downdraft and lead to strong winds. The 3 leftmost sets of bars here refer to relative humidity at 850, at 700, and in the average in the subcloud layer. Really, 700 relative humidity works pretty well with the driest environments giving you the high intensity severe, moisture environments no severe. The subcloud humidity doesn't work very well at all, and the 850 is also not very good. On the right side, lapse rates in both the 700 to 500 millibar layer and 850 to 500 also work pretty well to distinguish between the types, although probably not as good as CAPE, but they do still have statistically significant differences. Finally, with shear. So on the left side, the U and V components of the 0 to 3 kilometer shear vector. Toward the right, we get into parameters generally dealing more with deeper layer shear, except the fourth set of diagrams would be the magnitude of the 0 to 1 kilometer shear. But really, the low level shear works really well to distinguish the blue box, the non-severe cases, from the severe. But the blue and orange pretty much show almost no difference. So low level shear doesn't tell you if it's going to be a marginally severe or a high intensity shear situation. But 6 and 8 kilometer shear and shear magnitude seems to do a better job of differentiating between all three types of severity. And then finally, all of the composite parameters that we looked at work really well at differentiating among these severe types, whether it be supercell composite on the left, SIG-TOR in the middle, and the Evans-Derecho composite parameter on the right. Very strongly statistically significant differences among the three severity types. So we decided to look at using thresholds. There was a paper many years ago by Reams that did something like this for tornadoes. I think it for day and night. So here we decided, what kind of Heidke skill score would you get if you used a single parameter as a threshold? And we found that most unstable CAPE works really well, as do all three composite parameters. So in this table on the left, you see SIG-TOR parameter, if you use a threshold of 0.589, works the best for predicting the high intensity severe, and the Heidke skill score of 0.45 is really good. This is almost twice the best skill score I think that Reams found for tornadoes. But if you add in two parameters, you can improve your Heidke skill score by about 20%. So here at the very top would be surface-based CAPE above 657, and the 6 kilometer U component of the 0 to 6 kilometer shear vector above almost 30 knots works really well. Well, that CAPE value might seem pretty low to you, like you'd have a lot of false alarms. But if you look at a plot like this, which has the Gaussian density kernel estimates on it, and the colored dots refer to the type of event, even though the CAPE value, which is the vertical line of 657, might seem pretty low, like we know we get some weak convection that would have more than that value of CAPE, most of these weak situations, the green or the blue dots that have CAPE greater than that, end up having shear less than that value of 29.8. So if you look at the quadrant in the upper right, these are the thresholds that gave us the best Heidke skill score, and you can see that captures almost all of the orange dots while keeping very few dots from the other types of events. We also have looked already at what happens using parameters as a threshold for no severe. So here, the threshold would be everything less than that. And we actually get even better Heidke skill scores around 0.60 with SIG-TOR. So now the SIG-TOR value, when I saw this, I thought this was ridiculous. It's, the threshold's 0.04. Well, it's really tiny. And if you look at double two variables, the situation that worked best, and again, it improved the skill score by about 20% over using just one parameter, is an Evans-Derecho composite above below 1.27 with a storm relative helicity below 243. Well, 243 is a pretty big storm relative helicity if you're using that to say when you're not going to have any severe. But if you look at a chart like this again, you can see why it really works well is, even though you do get many severe cases that have less than 243, these severe cases all end up having an EDCP greater than 1.3. So on this picture, for forecasting non-severe, it's the lower left quadrant that happens using these two thresholds. And you can see a lot of the no severe cases have a very low Evans-Derecho composite parameter. This is also what ends up happening when you look at that single parameter of SIG-TOR that seemed like a ridiculously low threshold. The SIG-TOR tends to be really low in these cases. So just to conclude on this look at this ongoing second project, 31 of the 43 parameters tested had statistically significant differences between at least two of the three bow-echo wind severity types that we studied. The best discriminators for all three types tended to be the composite parameters and CAPE-based parameters, all of which are higher for the most severe events. Low-level shear only discriminates between non-severe and severe. It doesn't really tell you how intense the severe would be, but the deeper layer shear parameters discriminate better among all three types. SYN and near ground stable layer characteristics do not really vary, and you can actually get high key skill scores that are really high for parameters like SIGTOR for both above a threshold for high severe and below a threshold for no severe. And adding in a second parameter improves the high key skill score in both cases by about 20%. So I will end just mentioning the 2 grants that are supporting the research, and I would love to take questions. I know during the SFE, the first project in particular, there was a lot of interest in that one. So feel free to fire away questions if Justin thinks it still works time-wise.